and go from the current slide. All right, just a couple of announcements I'd like to make before we get started. First, to deal with the class. Glad the two of you are here. I hate being here talking to myself again. But we did get our first paper in. Way to go. And it was good to see. But that means 6 people have not turned in a paper with less than 2 weeks remaining. Okay, so please, folks, let's get those papers in. That means you only have 2 weekends left to work on it if you work on weekends. First test, I did get all those in. Say again.
Our exams was the first week of July.
August?
No, first week of
Yeah.
August,
No, you already had it. No. It's, yeah, well, actually, it's going to be a take-home exam. So last day of class, I'll give you the exam to turn in anytime that week. So, I think I returned these to you the other day because the last one came in 1 or 2 classes ago. And you've got your second test, right? Busily working on it, right? All right, good deal. Huh? Okay, cool. All right, and then we'll get as far as we can in chapter 4, and that's probably going to be all we're going to have time for. There are some sections in chapter 4 we're not going to do because some are optional sections. Either do this one or that one is how the book presents it. So we will go from here. Now, that's class type stuff, announcement. This next one, this is a big deal to me. I hope it will become, if it is already a big deal to you. Today is a voting day, right? Runoffs, okay? You didn't even know, huh? All right. What's that?
I've seen all the commercials, I just don't know when it was.
All right. Yeah, today is a runoff, and if you voted in the primary, then you have to vote in the runoff for whichever party you voted in the primary. But if you didn't vote in the primary, you can select either ballot, okay? And what's that?
Did they just pass that law this election season?
It's, well, actually, I think it was last time too. It's been recent, though, you're right, that you can't cross over and vote in a different runoff from what you had the primary. So, but if you didn't vote in the primary, you get to choose your ballot. So please vote, okay? Do not let a voting day go by without participation. My wife showed me on the internet, in the last presidential election, the leading candidate had 65 million votes. The number 2 candidate had 62 million votes, and 90 million eligible voters did not vote. And that was in a presidential election. That's the plurality didn't express an opinion. They basically got what they deserved. I mean, it's just, I'd far rather, if I were running, lose by 2 percentage points when 90% of the people voted, almost than win by 5 percentage points when 25% of the people voted. And 25% is not an unlikely figure for a runoff on the primary. It is, I mean, it's sick that 13% of the electorate can choose a candidate. That's not a democracy. So please, please vote today. You got time. I'll be teaching until 5:30. I have office hours till 6, but I have time to get home and vote before 7 o'clock. So please vote. Now, if by chance you're not registered, you can't vote today. But you can get registered and vote in November. And please, please vote in November. Vote today. Vote every time those polling places are open. Sorry about that. But I wanted to get that on here too. All right. Any questions on anything we've covered so far? Okay. Back on the voting, one of the phrases I like to say is, If you don't vote, you have no right to gripe. And I like to gripe, so I want to make sure I vote so I have some sort of right. Either the other guy wins and I can really complain, or my guy wins and they don't do what they said, I can complain. So, but if I don't vote, I have no right to open my mouth. Okay, never mind. It's hard for me to get off of that. All right, we left off last time in Chapter 4, Higher Order Differential Equations, in Section 4.2, called Reduction of Order. And let me just remind you where we're coming from here, okay? Now, in 4.1, we talked about higher order differential equations. First, homogeneous, and then non-homogeneous. In this section, we're starting back with the homogeneous case, and you'll see in the next section why we start here. Because when you're solving a non-homogeneous, you start in the homogeneous case. So we always, in our higher order differential equations, especially those that are linear, we always start with the homogeneous case. Now, the general form they listed at the top of 132 we did last time of this general, they say solution, but the general form of the linear second order differential equation is this. A sub 2 of x y double prime plus a sub 1 of x y prime plus a sub 0 of x y is equal to 0. Okay? That's a linear second order ordinary differential equation. Okay? In its most generic form. These coefficient functions are indeed functions. They say of x, they could be constants, and in the next section we'll look at the case when they are constants. Okay? But in general, they could be a function. Okay? Now, that's kind of the generic form of this differential equation. When you have it in that form, though, it's often better to do this. Just like we did in the linear case. Okay, time out. For this to be a second order linear differential equation, right? For that to be a second order linear differential equation, the a2 of x cannot be 0. It could be a constant. It could be a weird function of x alone, but it cannot be 0. Why not? Because if it was 0, that's a linear equation. And we're assumed from the assumption this is a second order, a first order linear equation. We are assuming it's a second order. So therefore, the a2 of x cannot be 0. Now, since it cannot be 0, we can do this. We can divide every term on both sides of the equation by a2 of x, because we know it's not 0. Sorry, I put the parentheses in the wrong place. Okay. Divide this one by a2 of x. Okay. You can even divide 0 by a2 of x. And that divided by anything other than 0 is still 0. So this goes to 1. So now our new equation, linear, second order, ordinary differential equation, would be y double prime plus, now, this is a ratio of two functions of x. So this could be a rational function. We know the denominator is not 0, but let's just give it a new name. And if you remember from before, we're going to give it a very familiar new name, like capital P of x, okay? And that's going to be the coefficient function for y prime. And then we'll have, and let's just, since we're naming new things, let's just say this one is q of x, okay? Times y, and that's still equal to 0. Okay. Now, the only thing I don't like about this choice is that back in the old days, back in pre-calculus algebra, when we saw a p of x, and most of the time a q of x, we were assuming then polynomial function. That's what P of X stood for. Capital P of X was always our polynomial function. Remember, this is not necessarily a polynomial function. Just by its definition, it's very likely to be a rational function, which is not polynomial. So don't get those confused. All right. So there's our new form. It's just as generic, just as good, and we're going to call that the standard form for a linear second order homogeneous ordinary differential equation. Okay, can I get all the adjectives in there? All right. So, since we've got that, here's a sort of a dumb assumption. Okay, oh yeah. Here's something that's required. P of X and Q of X, even though they could easily be rational functions, they need to be continuous on some interval I. Okay? That means that even if they might have say a vertical asymptote somewhere, or just a hole in the function somewhere, or something that is not continuous, you have to have an interval over which both P and Q are continuous. Okay? Quite often that's difficult with rational functions, but, I mean, not difficult, you just have to choose your interval well. But we're going to make that assumption that these are both continuous on the interval that we're dealing with. So let me put this down. P and Q continuous on I. Okay? If you understand what that means. Okay. Now, here's the other assumption that is really bizarre. Okay? But there's a reason for it. Let's assume further that we know one of the solutions. Okay, now first, back off. What is that going to produce? When you have a second order linear ordinary differential equation, what is your general solution going to look like? Okay, yeah, you're going to have a superposition of two linearly independent solutions, y1 and y2, and y1 may be multiplied by c1, y2 by c2, you know, that kind of, yeah, we know what it looks like. And here's a dumb assumption. Let's imagine we know what y1 is. Now, how we know that, I don't know, but that's going to be our next assumption. Let's assume that we know that y1 of x is a solution. Okay. Now, a known solution of that differential equation on this interval I, okay, and that y1 of x is not equal to 0 for every x on the interval. For every x on I. Okay? So there's another assumption, that y1 of x is not 0 for every x on the interval. Oh, boo hiss. Because usually the easiest function to pick out and say, oh, I know that's a solution, is a trivial solution, right? Because you know the trivial solution is always going to work there. But we can't choose the trivial solution because the trivial solution is y equals 0 everywhere, and this can't be y equals 0 anywhere. So don't choose the trivial solution for your y1. And that's going to be pretty obvious later too. All right. Now, if that wasn't bad enough, let's say that the next solution, we're just going to call it y of x, is going to be some u of x multiplied by y1 of x. Now, they don't make a point of this, but I think you've got to do this. Okay? Remember here, I said these A1s, A2s, A0, P of x, Q of x. Guess what? They could be constants. They don't have to have x dependence, but they could. That's why we generally put them that way. This one, however, I think is absolutely mandatory that have a x dependence. And here's why. If u of x was just a constant, then this y is just a multiple of that y, right? And guess what? They cannot be linearly independent. What we're going to do later, not yet, later is going to require them to be linearly independent. So this u of x has got to be some function of x. Now I can't prove this to you just standing here talking, but my gut feeling is if you have this solution and you multiply it by a u that has an x dependence, then you automatically are going to make this one linearly independent. If that was a constant, no. But if that is not a constant, if that has x dependence, you automatically are going to make that second one linearly independent of the first. Okay? Now, I can't prove that, and they don't bother with it, but I think that's going to be the case. Okay. Now, what are we going to do? If we know that y1 of x, okay, is a solution for that differential equation, and we're going to define some new y, which is u of x times that y1 of x, and what we're going to do is let's see if that new y might be a solution. Okay? Now, it seems a little bizarre, but let's do it. So if we know that y of x is u times y1 of x, then and we want to plug it into this form right up here, and they call this form 3, so let me call it 3 so we'll know. And the original form up there was 1, so if we need to do it, we'll come back and refer to that as 1, okay? So if we know that's y of x, what is y prime of x? Anybody? Okay, u of x, y prime, y1 prime of x, is that what you said? Okay, plus u prime x, y1, not prime, y1. I put my 1 up top for some reason. Okay. Okay. All right, there's your y prime. What's that? Oh, yeah, that's u prime. You're right. Good, thank you. Okay. Now, we're also going to need y double prime, right, to plug in there. So what's your y double prime of x? U of x, y double prime x, y1 double prime x, I keep forgetting that, plus u prime x, y prime 1, y1 prime of x, okay, plus u prime x, y1 prime x, plus u double prime x, y1 prime x, right? Now, okay, you're right, I was looking at the wrong line. Okay, thank you. Okay. Okay. Now, let's see if we can simplify the other one. Now, I'm tired of writing the of x's in there, so I'm going to simplify it by leaving those out. So this is going to be y double prime is equal to u y1 double prime plus, and here we have a u prime y1 prime, and there we have one, so we've got two of those, 2 u prime y prime, and we've got a plus u double prime y1, right? Okay, now let's plug in these values to our differential equation. The first one's going to be exactly what we got there, u y1 double prime plus 2 y1, wait, I've got them backwards,
2 y1 prime u prime, it doesn't matter which order you write them, plus u double prime y, plus p, I'm going to leave off the x's now too, okay, just because I don't have room to write them all, time your y prime, and here's your y prime, that would be p, u, there goes the x in there, it's trying to sneak its way back in, okay, p, u, y1, oh, I left off my 1 there. Yuck! Okay. y1 prime plus pu prime y1. Okay? Plus q times y, and y was simply u y1. And if that's indeed true, this is equal to 0. Right? Now, I want to point something out to you. We knew that y1 was a solution. And if y1 is a solution, then, well, let's do this first. Let's get all the u terms together and all the non-u terms together, if that makes sense. This would be u, I say u and write y. There's something wrong with my brain here. Okay. All right. Let's try that again. U, y1 double prime, plus p u y1 prime, plus q u y1. Right? If it would ever write. There it goes. Now let's get the the non-u terms together. And that would be plus, I'm going to rearrange them slightly, u double prime y1. This is driving me nuts. Okay? Okay, let's check them off. We got that one, and that one. I just wrote this one down. Okay. I don't think it matters too much. So, good. Here's right, right? All right. I think you were here last time I returned the first test to you, right? Okay, good. Okay. We're on page 133, that's chapter 4, higher order differential equations, 4.2, reduction of order. Not that we want to reduce any order in here, we want to keep it very orderly. No, I'm just kidding. Okay, and we're at the top of page 133, section 4.2. Okay. I'm rewriting this equation here, which we had just filled in from here. There's a lot of background to it, so you have to sort of pick up on it. I don't think it really matters here, so I'm going to write this. Plus 2 y1 prime u prime. And here's Monica. And now, all of you are transient students, right? You're not Lawson, or are you Lawson students? Huh? You're Lawson. But you're both transients, right? I thought of you last night when my wife was reading me something else off the internet. There was a news article yesterday about a Lawson student named Carr was his last name. And I can't think, I said, no, I have a Carr in my class, which it's Monica Carr. And I looked it up. No, it's Monica Carter, and that's why your name came to mind. He did a very extraordinary thing over the weekend. He had just gotten a new job.
You know him?
Huh?
He was walking to work.
Say again?
Was he walking to work?
Yes.
Anybody walking to work?
Yes.
He goes here?
Yeah, I think he goes to Birmingham campus. I don't think I've ever had him for a class. But that kid, as a Lawson student. Did y'all hear the story?
He wanted to come home.
He got a new job. He was supposed to start sometime over the weekend. I don't remember which day it was. And he was supposed to be at work at a certain time early that morning, whatever it was. And the night before, his car died. And he had no way to get to work. He really wanted the job. And he lived in Homewood, and the job was down, he thought, in Pelham. So he started walking. He got 4 hours sleep before, started walking at midnight to get to the job site. And he started walking at midnight, and in 2 hours had made his way from Homewood to Hoover. And he was walking on toward Pelham, and a couple of police officers, in the middle of the night, 2 o'clock in the morning, and a couple of police officers pulled over and said, "Is everything okay?" And he explained the situation to them, and they said, "Wow." They gave him a ride, took him to a place for breakfast, a Whataburger or something like that. It was open 24 hours, and he had a burger for breakfast. They bought him breakfast. They hauled him to a church nearby to where his site was going to be, so he wouldn't have as far to walk. And then they went on back to the station because it was time for the change. Well, shift change. So he thought the church would be a safe place for him to be. So they went back to the station, and they told the people who were relieving him. So they went to the church to find the guy, and he had already started walking again. And so that police car, picked him up, talked with him, stuff like this, gave him a ride. They may have stopped again for him or something, but gave him a ride to the house where it was a moving company. So he got to the house way early, way before any of the rest of the company got there. And the police officers took him to the door, explained to the lady of the house, who was already up, packing, getting ready for the movers. And she was so impressed by his work ethic that she said, "Look, why don't you come in, and if you want to take a nap, why don't you do that until the others get here?" He said, No, I'll help y'all pack. So he helped them get ready for the move, and they were just so impressed with him and his work ethic and everything else that when the rest of the crew showed up, she said, "Tell them what you did." And he was really embarrassed. He said, "Well, I just walked here. My car died, so I walked here." She said, "No, tell him the rest of it, that he had walked 20 miles to get to his job on time. First day on the job." And so they were really impressed. And somehow, and then she tweeted it, and it got out there on the public media. And then the president of the company up in Nashville, Tennessee, saw the tweet, saw his company mentioned, and stuff, this new employee. So he drove down to meet and congratulate the new employee in a 2014 car that he owned but hadn't used a lot. And he said, "This car is yours." Gave him the car because he was so impressed with his work ethic. And the guy was just, they said his comment was one word: "Seriously?" That's all he said, So I got so proud of Lawson State last night. So Karen did. Yeah, Karen found it somewhere, and she said, "I think he was a Lawson student." And she read the article again. There it is. Yeah, he's studying. He wants to go in the Marines, and but when he gets back, he's a health science major here. He wants to go in the Marines, and when he gets back, he wants to get into physical therapy and do his bachelor's in physical therapy or pre-physical therapy or whatever. That's what he wants to do career-wise. And so I said, I probably know his advisor. I don't know him personally, but anyway, sorry about that. That's not differential equation. Okay, let's get back to this one. All right, so what we're doing is writing down these terms. There's that one. And here's one with plus P. Yuck. U prime. This is driving me nuts. Y1 plus, and that's the last one. And supposedly this is equal to 0. Okay? Let me make sure I got them all in there. I think I did. Yeah. All right. Now, there's a reason I did that. breaking them off this way. And that's this reason. I'm going to factor out a u here and make this u times y1 double prime plus p y1 prime plus q y1 plus u u double prime. If I could get it to right, there it comes there, okay. Y1 plus 2, okay, y1 plus p times u prime am I missing a term? No, I guess I got them all. Yeah. Is equal to 0. Okay. Yuck. Okay. Now, the reason I wrote them this way is this. Look at that. That's exactly, remember we said y1 is a solution. And if y1 is a solution, then this thing right here is equal to 0, right? So therefore, we can just say this is 0. Just wipe that out. Okay? And what do we have then? We have u double prime y1 plus 2y1 plus p u prime is equal to 0. If indeed that new thing is a solution. Okay? I think I left off a prime somewhere. Or else they put one extra in. Let me see. Y double prime. Okay. It's equal to u times y1 double prime plus p1 q1y plus y1 u double prime. They call that a 2 y1 prime. Yeah, it is. I've got to find, yeah, see that's a 2y1 prime. There it is there. I forgot my prime there. And that makes that a prime there. Okay. Plus p, I left off the y1 here. Okay. That p is time y1. I factored out the u prime, but I forgot the y1. Okay, there it is. Now I've got them back in there. Okay, everything's copacetic now. Okay, that means that's equal to 0. Yay! Okay. So, well, what does this mean for us? Well, we've changed from a function of y prime, double prime, y prime, and y's to u. But notice the u is only at the double prime and prime. There is no u in here. The u got put up here, okay? All the u's got put up here. So, and that then went to 0 when that was equal to 0. So, what this means is now we can reduce the order of this by making up another new variable. Why not? We just love making them up. We made up the u. Let's make up the new one. And this new one is going to be w. Okay? So let's let w equal u prime. Okay? Now, I think what I need to do is erase most of this because I'm not going to have a lot of room. So let me try to selectively erase some of this stuff. I don't think I need this anymore. I hope not, but if so, I'll reproduce it. It's not that hard to do. Okay? And I hope I don't need this, but I'll remind you of that if that's the case. Okay. Maybe I'll keep that one. Yeah, why not? And I think I've used this to death, so let's get rid of it. I don't know that I need that line up there, but we've used this. Okay. And we need that still, so let's hang on to that. Don't think we need this line. Okay. Don't think we need this anymore, but if we do, we can reproduce that pretty easily. It's ugly anyway. And I think we can lose this because we pulled out of it what we need. Okay. Now I think the rest of them we're going to hang on to. Well, maybe not this. These. I don't need these. Okay. Sorry, this takes longer than it's worth, but I want to leave the pertinent stuff on there. And I need more room to write. Okay. All right. So what we've said was let W equal U prime. All right. Now, here is the equation we're dealing with, this one right here. Okay. And if we let W equal U prime, I think I'll come up to the top and start writing here. Then U, then what is W prime? Pretty easy. U double prime. Got it. So instead of U double prime, we're going to put, I'm going to start with the Y1. Y1 U W prime, okay, plus 2Y1 prime plus PY1 times, and U prime is W, is equal to 0. All right. Now, that equation, and I left, yeah, I got it all in there. Okay. That equation, by the way, is linear in W. First order, that's our reduction in order from second to first. And not just that, it's separable. Okay? So what we're going to do is separate out the W's and everything that's not W. Okay? I think. Is that how we're going to do it? Okay. So this will be Y1W prime plus I think before we do that, I'm trying to think the order that will make the most sense. Let's kind of separate before we divide. That sounds stupid, but in other words, let's divide this term by W. Okay, that wipes out that W. And everything else we'll divide by Y1. Okay, so that wipes that out. You get a Y1 here. So what do we have now? W prime over W, I'm going to move it to the other side, is equal to minus 2y1 prime over y1 minus p. Right? I believe that's right. Okay? Now, they left it all on one side. I separated. Now, the next thing is rather strange, and I'm now sort of wishing I kept a little bit more in. Remember, u is a function of x. That makes w a function of x. Y is a function of x. So the y double prime and the y's and everything else, y1, okay. I keep doing this and y'all let me get away with it. That's a y1, not a y prime, okay. Sorry. The ones and the primes look alike and I keep putting them in the wrong place. Okay. If we're integrating this, we're going to integrate with respect to x. Okay. So we'll put a dx here. And let's go and put a dx here and a dx here. Okay. And integrate both sides. Okay. And you see we're really separating three things. The w's are separated. The y's are separated, y1s, and then the p of x is separated. Okay? So that's what we've got. Okay? Now, I kind of now wish I hadn't separated the way I did. Let me change one thing here. Sorry about this. Let's take out the equal sign here, leave this as a plus, and make this a, sorry about this. That's a plus, and make this the minus integral p dx. Okay, there it is. There, I think I've got it now. Now, what is w prime over w? Integral of that? ln w. So this would be the ln of w. And we'll put absolute values just for now. Okay. How about this one? If I pull the 2 out, say again, 2 ln y1. Right? And we'll put that in absolute values too. And that's equal to the minus the integral of p of x dx. I'm not going to write the of x, I started to. All right? Now, we can fiddle with this a little bit. Take this 2, remember a rule of logarithms? Take the 2 here and make it an exponent there. Right? And then a sum of two logs is the product of their arguments, right? So this becomes w y1 squared is equal to minus the integral of p dx. Okay. Now, we integrated, we didn't integrate that last one, so we really do need a constant out here. We'll call it c. Okay? Now, let's take the, and these probably should be in the absolute value bars. Okay. Now, let's exponentiate, wait a minute, I left off my log of that mess, okay, of that stuff. Okay, log of the sum of two logs is the log of the product. So now let's exponentiate. That'll get rid of the log. That gives our w y1 squared is equal to minus, okay. If we exponentiate this and exponentiate that, then we can combine the two and make it a minus C, and they call it C1. No, I'm sorry. C1e to the minus integral of p of x dx. Now, my question to you right now is this. Does that look a little bit familiar anyway? Remember when we were doing linear equations? Say again? Yeah, when we were doing linear equations back in 2.3, I think it was. When you did all that other mess, remember? We wound up with, let's take that middle term, the p of x, that's why they use p of x this time, integrate it and raise it to the e. That's going to be their, they call it the integrating factor. Okay? Well, here we have something that looks very similar to that. We're not yet going to call it an integrating factor, but if we solve this last equation for w, then we're going to divide by y1 squared. Okay? And if we do that, that's what w is. Well, w is u prime. So du dx is equal to c1 e to the minus p of x dx over y1 squared. Which means now we integrate that with respect to dx, and we get u is equal to this thing. The integral of, let's put the c1 on the outside, e to the minus p dx over y1 squared dx. And since we integrated the left-hand side, we need another plus c. That'll be a c2 out here. Now, there's what our u is. c1, the integral of e to the minus x dx over y1 squared dx. I already said the d. Why do I? Oh, yeah, the r2 dx is in there. I missed my integral sign there, okay. Integral of p of x dx. Then this dx goes with that integral, and there's your c2. Oh, isn't that a beautiful form? Well, my writing isn't very beautiful. So let me rewrite it. U is equal to c1 times the integral of e to the minus integral of p dx over y1 squared dx plus c2. All right. Now they do something that always gripes me like crazy, because I don't see why they are enabled to do it, but I guess it's fine. They say, well, let's just choose C1 to be 1 and C2 to be 0. Do you have that option? I guess you do. I guess they're arbitrary constants, so they can be anything they want to. So they let C1 equal 1 and C2 equal 0. So basically, you lose your constants, okay? Which almost made me wonder why we brought them up in the first place, okay? So anyway, there's our U, okay? Now, I think Curry was having a flashback to the same thing, because before we called it mu, the integrating constant. Now we're calling it u, the kind of a new integrating constant. So your y2, oops, still have that, y2, which is the second function, y1 was one solution, and y2 of x, I'm going to put it back in there, is equal to u, which is is y1 right here. y1 of x times u of x, but the u of x is this thing, the integral of e to the minus p dx over y1 squared dx. Okay. Now, I didn't put my of x's in there, but I could have. Now, what they say, it makes a good review of differentiation to verify this function y2 defined in this equation satisfies that very first one we had, you know, that was the y double prime plus p of x, y prime plus q of x, y. And then also to show that y1 and y2 are linearly independent on any interval in which y1 is not 0.
Well, of course we see one reason y1 can't be 0, right? It's in the denominator, so it can't be 0. It would also not be 0 because then y2 would have to be 0 because y1 is, u times y2 is u times y1. So y1 can't be 0, and there's your thing. So it's not quite as simple as it was before, but it sure is awfully close. Remember that form? Looked a lot like the previous form, but now we have two solutions. One's a y1, and then y2 depends on it. Now this is some function of x, and this function of x is going to make it so that this is not linearly dependent on y1. It can't be a constant. It's got to be a function of x. Okay?
Now, finally, all that, we're ready for example 2. Okay? So, what I think I'm going to do is erase most of this. Okay? We've used our W's and changed them back to U's. We changed the U's back to Y1s. So we don't need any of this anymore. That was just getting us there. I think all we need is the last. Now, still got a little bit of a problem. We had to know that there was some y1 that was a solution, and we don't know how we knew that yet, okay? So, hopefully, we'll be able to finesse our way around that, okay? We'll see. I should have just written that down again. Okay. Now, example 2. Here's a function. Oh, they tell us. The function y1 is equal to x squared, they say is a solution of x squared y double prime minus 3xy prime plus 4y equals 0. It says find the general solution of the differential equation on the interval 0 to infinity. Okay? Now that would be interval of x's. Okay? And if x can't be 0, and this would be find the general solution. Find general solution on 0 to infinity. Okay, so if x can't be 0, certainly y1 won't be 0. We've taken care of that. You knew y1 could not be 0. Okay, so that part is taken care of. Now, first thing I want to do, because I'm a cynic, I want to make sure y1 equal x squared is a solution for that differential equation. How do we do that? take a derivative, and that would be pretty easy, 2x. And we also need a second derivative, and that would be 2. Okay? So let's see if that indeed works. If y1 is a solution. This will be x squared times 2. So I'll make that 2x squared. Minus 3x times y prime. y1 prime is 2x. So that'll make this a 6x squared, right? Plus 4 times y, which is x squared. What does that equal? 2x squared minus 6x squared plus 4x squared. 0. Good for them. They got it right. Okay? They did find that was a solution. We showed it was a solution. They told us it was. And we just verified it. Now, to me, why do all this? Why aren't they showing us how in the world we find those solutions? That's what they're going to do next. But my word, they're taking their sweet time to do it. Okay? So, we know there's a solution. Okay? Can you come up with a second solution? y2. We'll call it of x. And what will it be? Oh, we got to do something first. Remember, this isn't quite in standard form. What do we need to do to get it in sort of our new standard form? Divide by everything by x squared. Okay? So our new form is going to be y double prime minus, you tell me, three over x times y prime plus 4 over x squared times y is equal to 0. That's our new form. Okay. Now, by the way, on the other thing, you ever notice the q we never used again. Once we say, oh, that's 0, it's gone. You know, that big term was 0. We're only using our p. Now, so for funsies, what is our p of x in this problem? Negative 3 over x. You're absolutely right. And note, on the interval 0 to infinity, perfectly legitimate. No problem there at all. Okay? So, let's proceed. I don't want to start with this yet. Okay? I wrote it, but I don't want to. I want to start with my p of x minus 3 over x. First thing I want to do is do the e to the minus integral of minus, that's going to be a plus then, 3 over x dx. Okay? And what's that going to be? What's the integral of 3 over x dx? That's 3, yeah, okay, ln x cubed. I was going to do it in 2 steps, you did it in 1. Fantastic. This one we never put a plus c there. Don't bother with that. What is e to the ln x cubed? X cubed, you're absolutely right, because an e undoes a log undoes an e. So we're left with just the x cubed. So there's that first part. Okay? Now let's do the integral. The integral we have here is e to that thing, which is x cubed, over y1 squared, but y1 was x squared, y1 squared would be x to the 4th. So this would be over x to the 4th dx. I think we can do that one too, can't we? And what would that be? ln x. Okay? So now we have y y2 of x is equal to y1 of x, which was x squared ln x. Okay? Done. There's our second equation. First question for you. Is this linearly independent from that? Yes, absolutely. There's no way you can add those two together and get 0 with any combination of c's unless both c's are 0. So that is linearly independent. Okay? So what's our general solution? That's what it asked for. Find the general solution. What's our general solution? Y is equal to, you can put y of x if you want to, is equal to general solution. Anybody? Okay, C1 x squared, the general solution has the constants in it, plus C2 x squared log x. Done. There it is. I sure hope so anyway. Yep, C1 x squared plus C2 x squared log x. Very good. Okay? Any questions on that? All right. And by the way, that's good on, look at this answer, x has to be positive, can't be 0, can't be negative. That's excellent to happen. Why? Log of 0 is not defined, log of a negative number is not defined. So that's an excellent interval of, and this is good everywhere on the interval. Everywhere on the interval. Just not good at 0 or any negative number, but that's why we had to restrict our domain. All right, good deal. That finishes 4.2, finally, okay? They have a little blurb back here on the remarks that basically is tying. No, I thought it was, but it isn't. Okay, never mind. Okay. We'll get to that later. Okay, 4.2, do any of the odds 1 through 15. Do either 17 or 19, and do 21. Okay? 21 may require something for the remarks, but if you, well, I'll let you figure that. The discussion problems usually don't have answers in the back, so I would say if you are interested in pursuing them, pursue them, but otherwise leave them alone. So let's get ready for 4.3. Whoops, wrong thing. Okay. Let's take a quick break. I was just going to suggest that right now. Let's take a quick, I'm sorry, I erased that. I hope y'all didn't need it. Let's take a very quick break. I need to walk some. Oh, walk down the hall some too. If I get back in less than 5 minutes, I'll get up and run. say this before I turn on the recorder again, but I think I ate something over the weekend that kind of disagreed with me. So my stomach isn't quite back to normal yet. Sunday wasn't too good. Yesterday was much better. Today, I think it's better, but I could at any point say, "Excuse me," and go run that, or waddle down the hall or something like that. So anyway, I hope I don't have to. And I did record that because I didn't take off the recording. Sorry about that. Yuck, I thought I had put it on pause, but I guess I did not. Sorry. Okay, let's move on to 4.3. Homogeneous linear equations with constant coefficients. I told you this was coming, didn't I? Okay. Now, it says here, as a means of motivating the discussion in this section, let's return to the first order differential equations, more specifically to homogeneous linear differential equations, ay prime plus by equals 0. Okay? Where the a and b are not functions of x, but are constants. Okay? Now, and of course, to be a first order, a can't be 0. Okay? Remember, that's always the case. If it's a first order differential equation, a can't be 0. Okay? B could be any constant in the world. A could be any other constant. Okay? That type of equation can either be solved by separation of variables, no sweat there, or with the aid of an integrating factor, but there is another solution method, one that uses only algebra. Okay? Now, and they say before illustrating that, here's an observation. Solving that for y prime yields this. Okay? Let's solve this for y prime. First thing I'm going to do is subtract by from both sides. Okay? And then we get a y prime is equal to minus by, and then divide both sides by a. Why is that legal? Why can we divide by a? A is not equal to 0. Very good. Well, the a's go out here, and then you have y prime is equal to some constant times y. We're just going to call it ky. Okay. Now, we just changed the b over a to some other constant k, minus b over a to k. Okay? Now, let me ask you a question. Can you think of a function whose derivative of that function is just a multiple of the function itself? E. And the way to get the multiple is make it e to the mx. And in fact, in this one, it would be e to the kx. That would give it to you, wouldn't it? If y is equal to e to the kx, what's y prime? K e to the kx, which would be k times y. Yeah, and you have exactly. Okay? Well, guess what? It happened to work for that k, which is minus b over a. But who cares what the numbers are? Anytime you have that kind of setup, this is going to be a good first guess. E to the, and they're going to call it from now on mx, not kx. Okay? Now, the only non-trivial elementary function whose derivative is a constant multiple of itself is the exponential function, and they're going to use m, and that's sort of standard, e to the mx. So, that's what we're going to assume is y is equal to e to the mx. That's going to be a solution, and then we'll go to town with that. Y prime is equal to what? m e to the mx, sort of ugly, okay? And then if we plug that back in here, we have a m e to the mx plus b e to the mx, that's the y, okay, is equal to 0, right? Well, if that's equal to 0, by the way, feature about exponential functions, can you tell me a few characteristics of the exponential function? E to the mx. M can be any value in the world. Exponentials are always. Second? Okay. Depends on the size of the m. If m is a number greater than 1, they're getting bigger. If m is less than 1, they're getting smaller, right? Okay? But guess what? They never equal 0. They're never negative. An exponential is always a positive number. Because what is e? E was some number, 2.7, blah, 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 blah. You know, irrational number raised to some power, and that number raised to a power is always positive, okay? Raised to a negative power is still positive, okay? So that is always positive. Never 0, okay? Remember the reverse of this is the log. You can't take the log of 0 because they're inverse functions of each other. So therefore the e can never be 0. Well, if it's never 0, let's just divide it out. Okay, and what you're left with here is a m plus b is equal to 0, and surprise, surprise, subtract b from both sides, and you have a m is equal to negative b, and divide by a, and you have m is equal to minus b over a. That's exactly what we had our k to be, right? Yeah, you can solve for m, okay? And first order, you only need 1 m. Second order, you're going to have an m squared. It's going to be a quadratic. Third order, you're going to have a cubic, okay? You'll have as many solutions as you need, okay? Now, the other thing to notice, we got an equation here that really looks a lot like this equation here, doesn't it? Okay. We have a, whereas this is m to the first power, that's a y to the first derivative of y, plus b times the 0th derivative of y, which is y to the 0. And that's equal to 0. So this equation here always matches your differential equation with constant coefficients. Because instead of your y's and y primes and stuff, you just put m's and powers of m's, right? This is called your auxiliary equation, okay? You can go through and do the let y equal e to the mx, and you're going to get that auxiliary equation every time, okay? And that's what we call it. am plus b is equal to 0, rather than ay prime plus by is equal to 0. That's your, that, and then you find the values for m. So let's see. Let me erase this and see if we can apply it. 2y prime plus 5y equals 0. First order linear differential equation, right? Can you just give me the auxiliary equation? If you can't, you can use the y is equal to e to the mx. To what? I couldn't hear. 2m plus 5 equals 0. There it is. There's the auxiliary equation, right? How do we get it? Let y equal e to the mx. Then y prime is equal to m e to the mx. And then you did 2y prime, which is 2m e to the mx, plus 5 e to the mx equals 0. Divide out your e to the mx, because that's never 0. You can divide it, okay? So 2m plus 5 is equal to 0. There's your auxiliary equation. So, of course, in that case, what would m be? Negative 5 halves. So, therefore, your solution would be y is equal to C1. You have to have a constant, e to the negative 5 halves x. There's your solution, okay? And that's good everywhere, okay? I put C1, they put C1 too. We could have just put C, okay? Now, with that in mind, let's go to a more general case. A very much more general case. A sub n, y, the nth derivative of y, plus a sub n minus 1 times the n minus first derivative of y, plus a to the n minus 2 times the n minus second derivative of y, plus dot, 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 all the way down to, let's do a sub 3, y triple prime, plus a sub 2, y double prime, plus a sub 1, y prime, plus a sub 0, y is equal to 0. Okay, there is the very general case of a linear ordinary differential equation, nth order differential equation with constant coefficients. All those a's are constants. Any constant in the world, fractions, decimals, positive, negative, rational, irrational, it doesn't matter. They're constants. With one exception, a sub n can't be 0. It can be any other constant, but not 0. The rest can be anything you want them to be. Okay? So the a sub i's are any real constants as long as a sub n is not 0. So, well, I thought they were going to do something more with that. They didn't. Now they go to a general, more specific case. A y double prime, second order, plus by prime plus cy equals 0. A homogeneous, linear, homogeneous, ordinary differential equation with constant coefficients. Okay? A, B, and C are constant. Okay? Now, if you want to, you can say, let y equal e to the mx. I kind of like to do that even though I know what the auxiliary equation is going to be. I think it's a good idea to write that down anyway so you don't forget where you got it. What's your auxiliary equation? Anyone know? Or do we need to step through the steps? It's easy to do. Let me know. Step through? Okay. What's y prime? M e to the mx. And y double prime? M squared e to the mx. So this will be a times m squared e to the mx plus b times m e to the mx plus c times e to the mx is equal to 0. And then what can we do next? Divide out the e to the mx. Okay? So what's our auxiliary equation? am squared plus bm plus c is equal to 0. Okay? So suddenly our differential equation became a quadratic equation. Second order differential equation became a quadratic. Now, what are two techniques for solving any quadratic differential equation? Factor if it's possible, and if you can't, quadratic formula, exactly. So that you could always get two solutions. Factor if you can. If you can't, do the quadratic formula. Okay? So, whatever it turns out, and you just were saying it, so let's do the quadratic formula. M would be equal to, what was that? You were saying minus B plus or minus the square root of B squared minus 4AC all divided by 2A. So that's actually two solutions. One is minus B plus the square root of B squared minus 4AC over 2A, and the other is minus B minus the square root of B squared minus 4AC over 2A. Okay? I can't write, but you got the idea. Okay? That's your solution to the auxiliary equation. Your solution to your differential equation would be y, the general solution would be y is equal to C1 e to the minus b plus the square root of b squared minus 4ac over 2ax, okay, plus c2 e to the minus b minus the square root of b squared minus 4ac over 2ax. Okay? There's your generic solution. Of course, if you could factor it, this will be a lot simpler than that. But remember, there are some deals that you know. If that b squared minus 4ac, and by the way, does anyone remember what we call that? The discriminant. Not determinant, but discriminant. If that thing happens to be 0, you only have one solution. We're going to get to that later. If it happens to be a perfect square, then this will be two rational numbers. Okay? That will be pretty easy to deal with. If it's negative, of course, you can't do it. Yeah, and we'll come to that later too. If it's positive but not a perfect square, then you have radical exponents. But that's fine too. You have two different radical exponents. Okay. Now, so what I was calling this is what the book is calling M1. This is what the book is calling M2. Okay? I think I got them the same sign. M1 is the, I just saw it. Oh, there it is. M1 is with the plus and M2 is with the minus. It doesn't really matter, but just to keep it the same. Okay. Now, I'm going to erase all this. Is that okay? Now, we're going to start with that though. When we have a generic result that your M1 is equal to minus B plus square root of B squared minus 4AC over 2A, and M2 is equal to minus B minus the square root of B squared minus 4AC over 2A. Now, we're going to have three cases here, okay? The first case is M1 and M2 are real and distinct. Now that's what I was talking about with our discriminants. They're real and distinct. Real meaning this is a real number. This is a positive number. B squared is greater than 4AC. In both of those. Then you have two real solutions. They're distinct because that's not zero. If that was zero, then they'd be the same answer, minus B over 2A. So real and distinct, meaning this thing in here is positive. Not zero and not negative. Okay? So there is your first case. These two, real and distinct. Okay? That's a pretty simple case. Okay? Here's your solution. Y is equal to C1 e to the m1x plus C2 e to the m2x. Whatever those real numbers are, there's your solution. Those are nice. Easy, manageable, really easy to deal with. Okay? Now, the second case. The M1 and M2 are real but equal. M1 and M2 real but equal. What does that mean? Is that the B squared minus 4AC is equal to 0. Okay? So, what are we going to do then? We only have one solution to that auxiliary equation. M1, because M1 and M2 are the same. Okay? Well, here's what the situation is there. Okay? Now, if you go back to section 4.2, and you may have wondered, why in the world did we do that? But we had that your second solution, okay, I'm stuck, okay. Second solution here is going to be some function of x times the first one. And if you look at example 2, that happened to turn out being a log x, okay? The remarks at the end there gave you some generic type help, okay? So, let's go back to example. Okay. All right. Remember this, okay? Your Y2, this is what happened when you needed that second thing, and you went through the, it's not quite an integrating factor, but came out there. This is what we wound up with. Y2 is equal to Y1 times the integral of e to the minus integral p dx, p of x dx, divided by y1 squared. And that's times dx. Okay. Now, in this case, I don't have my let me write this down so we'll see it. Remember, all this came from the fact, okay. What we had here was y M1 is equal to C1 e to the minus b over 2a x. Remember, that was our only one. When this thing here is 0, you have the M1 is minus b over 2a. So there we have it. Okay. Now, where that came from was y ay double prime plus by prime plus cy is equal to 0. But then we divided everything by a, so our p here, our p in this case, was b over a. Okay, so the integral of b over a dx is going to be b over a x, right? This is doing sort of crazily, but it is. So, and remember, our M1 is equal to minus b over 2a. So, if you multiply both sides by 2, you wipe that out and then negate it, and you have b over a is equal to minus 2m, m1. Okay, I don't know if that's helpful to you or not, but that's minus 2 times your solution there. And this, to me, this is, it does so much mess, okay, that it can almost get confusing. So it's y1, which happens to be I guess I'll put my C1. C1 e to the m1x, or let's just call it mx, okay? I think that's what they call it. No, they call it m1x, so we'll leave the m1 in there. And the integral will be this e to the minus, it's not minus, this is the minus, so minus the minus will be plus 2m1 e to the 2m1x, okay, over the y1, remember, was this, so that is 2c1 e to the 2m1x dx, okay. Well, the c1's go out, and what we have is e to the 2m1x over e to the 2m1x is just 1. So we have m1 e to the m1x times the integral of dx. And what's the integral of dx? This is a long way around to get there. What's the integral of dx? X. So our second solution, our y2, is equal to x e to the mx. I like to leave off the m1. So what's our general solution then? Can I erase some of this? Because it's really so much simpler than having to do all that over again. Your second one is just x e to the mx. Okay? There's your second solution. Okay. And I think I'll get rid of all that too. We used it, and we used it, and we abused it. You know, it's over with now. Okay? I don't think we need this either. Might leave that first one up there. Possibly. Okay? So, if those two are real but equal, then the m1 is minus b over 2a. So we'll just call it m1. So y is now equal to c1 e to the m1x plus c2 x e to the m1x. Okay? Yeah, and that's how they write it too. They like to put the ones in there. I don't see any reason to. So if that discriminant is 0 and you only have one solution to your auxiliary equation, one value, then it's the first one is that value of m, c1 e to that value m1 of x, and then plus c2 x e to the m1 x. Okay? So that's what happens if they're real but even. Now the third case, this is going to unfortunately take a while to do, so what I might do is just do it very quickly, and you just have to kind of buy it. What if the M1 and M2, in other words, the discriminant is now negative? Square root of a negative number you can't do in the real number system at all. So now they're complex. These two are conjugate complex numbers. I like to call them complex conjugates rather than conjugate complex numbers. The book has say it that way. In other words, your b squared minus 4ac is less than 0. Here it's greater than 0. Here it's equal 0. There it's less than 0. Okay? Now, that gives you a terrible mess. Okay? What your M1 turns out to be is it's a complex number, alpha plus I beta. Okay? This is going to come out an A. The alpha is going to be your minus b over 2a, and the beta is going to be whatever this imaginary is over 2a. Okay? Whatever the real part of that imaginary number is over 2a. And then the second one is going to be, your M2 is going to be alpha minus I beta. Okay. So those are your two solutions, and they are a mess. Okay. You could write this as y1. Well, let's just write it as y. Y is equal to c1 e to the alpha plus I beta x plus c2 e to the alpha minus okay, my writing stinks. Okay, I beta x. Okay, now those are not very friendly or useful forms. And by the way, a lot of books always write beta I, not I beta. I kind of like I beta for a reason. If beta was the square root, then I want that I to be outside. You don't think it's inside the square root. You know? So I sort of like this method better. This is not anything that's very useful. Okay? However, a good old guy named Euler, who would be a great paper topic, by the way, came up with an incredible number of things. In fact, his name is Euler, okay, Euler, okay, Carl, is it? No, Gauss is Carl. This is Leonard Euler, I think his name was, okay. I believe he may have been Swiss or German, but he worked all over the place. He worked in Scandinavia, Russia, he worked all over the place. But he came up with a bunch of incredible entities. In fact, have you ever wondered why E got the name E? Euler. He's the one who first defined the base for a natural number system, the E number, 2.7, blah, 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 blah. That was his number. He came up with it. He defined it, okay? And he did a lot of things with it. And here's one of the incredible formulas he came up with. E to the I alpha, theta, I'm sorry, I said alpha, theta, is equal to cosine theta plus I times the sine of theta. Okay? That's pretty incredible, isn't it? Okay? Now, so if you take this to be C1 e to the alpha times C2 e to the I alpha x, I beta x, we can do that. You know, if you're raising a power to a sum, that's the product of those two powers. Okay, and you can do the same thing here, plus C2 e to the alpha x times C times e to the minus I beta x. Okay? Now, if you take that last part, this one, and use Euler's formula on it, then let's do the first one first. E to the I beta x, okay, from this, that would be cosine beta x plus I sine beta x. And if you did e to the minus I beta x, because cosine is an even number, that still would be cosine beta x plus, or minus I sine beta x, okay? My eraser isn't showing up. There we go. Okay. Now, we're running out of time, I realize, aren't we? No! This thing won't, the pen now won't pick up. There we go. Minus I sine beta x. Okay? Now, notice we're adding these two together. This disappears. Okay? And what we actually wound up with is a new formula. And it takes them a long time to get there, and we don't have the time to do it. In fact, we're already out of time. Here's what it winds up. Your y is equal to, believe it or not, C1 e to the alpha x sine beta x plus plus C2 e to the alpha x. I got it backward. This is cosine. And plus C2 e to the alpha x sine beta x. It doesn't really matter. I just want to get it the same way they did in the book. Okay? So in other words, factor out e to the alpha x. So it's y is equal to e to the alpha x times C1 cosine beta x plus C2 sine beta x. Okay? There's your solution. A real solution when your m's were imaginary. Complex. Pretty incredible. Okay? We'll pick up with example 1 next time as we go. Let's see if you've got enough done to do any homework exercises here. I think you can do any of the odds 1 through 13. Okay? Now, some of those have negative discriminants, you can hang off on them until we do it the next example. Okay, but try to do some of those. Good deal. Sorry I ran over. We'll pick up next time with example 1. And next time will be Thursday. Okay. I have to remind myself what day of week it is. All right.